So you've emphasized mitochondria as the power plants of our cells. How does iron overload or copper deficiency disrupt mitochondrial function as we age? I know you talked about this in the previous episode, but I think it
Sure.
warrants some clarification again.
Yeah, the classical literature would tell you that copper is only involved in complex 4, which is called cytochrome C oxidase. That is where oxygen becomes 2 molecules of water. And that's where the energy molecules ADP get released to go over to complex 5 to become ATP. There's compelling research that copper is involved in complex 1, 3, 4, and 5. And iron is involved throughout the mitochondria, both in terms of its participation in iron-sulfur clusters, which are the physical infrastructure of these complexes are dependent on these iron-sulfur clusters. But also, the mitochondria isn't just a power plant, it's also a smithy. It's like, we are working with iron, and the mitochondria is where it's at, and the mitochondria needs to recycle the iron and turn it back into heme and back into iron-sulfur clusters. That process of doing that requires copper. You cannot make heme in the body without copper. 4 of the 8 enzymes are copper dependent. The iron-sulfur clusters are critical, or the rate limiting variable is called glutaredoxin 5. It's a copper dependent mechanism to allow the final stage of making the iron-sulfur cluster. So the process is that if the mitochondria doesn't have adequate levels of copper in the matrix and in these complexes, it's going to lower the energy production. And then what's also going to happen is the doorway, the iron egress doorway, which is called ABCB8, very important doorway in the mitochondria, is not going to open up. So the iron can't get out of the mitochondria. And what that mechanism does is allow iron to get into the cell so they can then leave to get back into the iron recycling system. And so ABCB8 is not working, ferroportin is not working, so you start to accumulate the iron. What's happening under stress is there's a rise in oxidative stress. Ideally, oxygen needs to be turned into water to release the energy. That's the obligate chemical reaction that's supposed to take place. Under stress, we produce 2 key hormones, adrenaline and cortisol. Well, we talked about adrenaline in terms of its ability to increase the production of hepcidin. That's not going to bode well for the mitochondria because it's going to keep the iron captured in the system. But the cortisol is going to increase the production of metallothionein, which is an iron-binding protein, metallothionein, that when triggered, it's going to bind up copper 1,000 times stronger than it binds up zinc. Well, that's a pretty important statistic to know, that it has this preferential affinity for copper under stress. And so under stress, we've got copper's being bound up, but iron is being accumulated in the tissue, and the energy production is dropping. That's a wicked combination. And so the goal is to recognize that you're under stress, see if you can change your lifestyle. That would be one obvious thing. Try to do emotional release techniques to release the fear that you're broken, or that you're stuck. That perception that I'm stuck, that I'm dealing with what's called restraint stress, is very damaging to the balance of the body and the mitochondria. And again, trying to restore the energy production in the mitochondria is really critical. And there you're back to the diet. We were designed to eat our meals sitting down, but not driving the car. Too many people, I think, are cutting corners, that they're in a hurry, got to get my meal. And we have to really step back from our lifestyle and say, am I allowing enough parasympathetic expression of rest and relaxation to deal with all this stress that I've got in my typical day-to-day life?
So you've answered the question I had about what we can do, especially in our 50s, 60s, and beyond, to support mitochondrial activity.